Here is the Math 2413 exam review, and we'll go straight to the topics. So the topics covered in the exam are as followed on the PowerPoint. If you need access to the PowerPoint, it will likely be under the description as a file, so you can go over this PowerPoint if you need be. Domain and range, these are kind of things that you should know already, but if you need to review them, they'll be on the PowerPoint. Same with interval notation and exponent and logarithm rules. So first unit should be tangent and secant lines. So tangent lines are kind of just lines that touch a point on the function, and they have a slope that follows the curve. So if you see this line, we have the tangent line touching this point and then following basically the slope that the instant that it hits this point. A secant line is different, where it needs 2 points and on the function and it cuts through. And what you can use with these is that secant lines can use to approximate tangent lines. So as we saw before, 2 points on a function, if you put them, or if you make them really close to one of the points, these 2 points will eventually be so close that they're essentially at one single point and they estimate a tangent line. So one of the functions you can use is that, you've probably seen it before, the slope is equal to the y value at the second point minus the y value at the first point, all over the distance between the two x values. And in these questions on the exam, you're probably going to be asked to use it, the slope, to form the equation of a line, and this is the equation here. So we're going to go through one of the practice problems. The point P2 lies on the curve y is equal to 1 over 1 minus x. This is the function, and this is the point. They're defining q as the point, as an x value, and the function. So we're going to use that, we're going to use that slope formula we found before for secant line. And we're going to draft up an equation that lets us calculate all these slopes. And so we have y2, we're going to use q. So q's y value is 1 over 1 minus x, and then minus -1, which makes it plus 1, and all over this qx minus 2. And so this is equal to our slope. So I'm just going to go through a few of these because for the sake of time. But we know that if we try the x value of 1.9, all we have to do is plug it in. So we do 1 minus 1.9 plus 1. And that's divided by 1.9 minus 2. You're going to plug into your calculator, and what you should get is 1.111 repeating. And if you try it with these other values, for let's say 4, do the same thing, you're going to get approximately 1.001001. Same thing with 6. If you plug in 2.1 to the equation, you're going to get an approximate slope that's very close to 2, and that would be 0.909090. And you do it again with 2.001, you'll get something like 0.999000. Right? And all these values are just to kind of lean towards having 2 points be extremely close together, so you can have a good estimate of the tangent line at this point. So that's pretty much B, which says use the results of part A, guess the slope, value of the slope of the tangent line at this point. And that's what we've been doing. We've been taking 2 points and then making them really close together. So we can find a pretty good estimate as just, I think, 1. Right? So m is equal to 1. For C, they want you to use that line equation, and that was y minus y. 1 is equal to m times x minus x1. We have that point being P, and we know that P is equal to 2, -1. And we also have the slope, which is equal to 1, which is what we estimated in part B. So we put that together and we had y minus, which turns into plus 1 because we have a negative 1 here, and times 1 times x minus 2. And I think you can keep it in that form, but you can also isolate the y and you get something like x minus 2, minus 1. And your equation would be y is equal to x minus 3. So that's for that problem. Same thing for velocity. Velocity is essentially the rate of change of position. And generally, you're going to get something like s of t, which is your distance function. And you're going to you're going to be asked to use that to find the average velocity for a secant line. Or the same equation for secant line can be used to find the average velocity, right? And instantaneous velocity is when you want to estimate essentially the tangent line for a point. And in this case, you're going to use the secant line or the average velocity to kind of estimate that instantaneous velocity. So we're going to skip over the tangent or the velocity question for now for the sake of time. But essentially, it's similar, as in you use these points which are given to you. So this would be your t-value and this would be your s function. And then you would use it. You would use the average velocity equation based on whatever kind of t-values that you're supposed to use. And you would plug these in, and you can use these values to kind of estimate the instantaneous velocity at this point. So these basically give you the kind of average velocities or secant lines around that point, and you can estimate. So example would be I-204 would be 29.3 feet per second. And for this one, it would be 25.9 feet per second. Oh, yeah, sorry, T1. So you could probably estimate around to be between these values. For the limit of a function, here's the textbook definition, but essentially what our limit is asking is if you have a function and you're asked to find a limit at a certain point, let's say a, you're essentially asked to find what number it approaches, but not quite. It doesn't have to be defined, but what function does it seem to be approaching for both sides? And one of the things you can also prove that is if the left side function or left side limit is equal to the right side limit, then the whole function should exist. And you can read these definitions if you need it on the PowerPoint, but that's essentially what a limit is. And if we try an example problem, you're often asked to find the kind of graphical limit, or using a graph to find a limit. So if we try A, this asks, what is the limit of 2 as you approach from the left side? So from the left side, you're going to follow the function, and when you hit 2, because it's not a full limit, it's a one-sided limit, 3 would be our answer. For B, it's asking for the limit as you approach 2 from the right side. If you follow the function, you'll get to 1. For C, this asks, so if you remember that equation from before, in order for the full limit to exist or equal to that number, they have the left side limit and the right side limit has to be the same. So A and B kind of show those two limits, but we see here that they are not the same. So therefore we conclude that the limit also does not exist, because the left side limit and the right side limit are not the same, that's it. and D is just asking for a point at f of 2. And as we kind of said before, for graphs, a dot will be a close, so it's defined, and a hole will mean that that point is not defined. So f of 2 will have to be the closed dot, which is at 3. For E, it's asking for a limit at 4. And we see here that if we follow the function from the left side till 4, we get 4. And we also have to do the right side, and it also approaches the same number. Now note that we don't have to have it defined, so the limit for this function as it approaches 4 is equal to 4. So for f, it's just demonstrating that your f of 4 does not have to be defined for the limit to exist, because there's a hole there, and therefore there's no point. So other kind of questions you might see is that you want to find the limit for certain functions. And for 31, you have to find the right side of this function. And in this way, we can kind of use a numerical method, because if we try to plug in 5, which is kind of the first thing that you try to do when evaluating a limit, you get some value over 0, which means that you can't compute the limit this way. But it doesn't. But because we have a one-sided limit, we still need to try to find what number it approaches from the right side. So for this way, you can try to find some value that's really close from the right side, right, of this number. So let's try just 5.001 and try to see where it approaches that way. So if we plug in our test value, you see the top doesn't really change, but the bottom will be a really small number, right? So this one will be something like this over some really small value. Oh, looks like we have students. Okay, but okay, I see some students coming in. So if there's enough students, maybe we can restart. Okay. So due to technical difficulties, I know you guys kind of came in late. So I'll try to review kind of a brief overview of what we just did. So it was supposed to be 45 minutes of topic review and then breakout rooms, but we might have to cut down on the practice rooms. Okay, so I'll just briefly review. And if you guys weren't here yet, we basically covered that these topics are just for if you want to use the PowerPoint. You should know these from last semester or any of the previous math classes. Briefly, tangent and secant lines are essentially certain types of lines you can use on a function. So tangent lines just means a line that is touching a certain point. Generally, you only use one point, and there's other ways to find out tangent lines later in the course. But for now, we're using secant lines, which require 2 points, and putting the 2 points as close as possible in order to estimate the tangent lines. And here are the equations that you need. This is a common slope formula. It uses 2 points, but you can make them really close together to find out a good estimate for the tangent line. And often, you'll use this equation, the equation for a line, to actually create an equation for that tangent line. Because when you use this, you only get the slope. And we covered briefly how to solve these tangent and velocity problems. I won't go over them because I think these are kind of self-explanatory. Essentially, you're using the slope formula, and you're given 2 points. In this case, they give you q in the form of variables. So you can just use that. That's what we did here. we put the y-value and the y-value for this point. We made an equation and we used them for all these values. And we use these parts, or all these values that are really close to 2, in order to find an estimate. Right? And then we decide it's 1, and we use that slope to create an actual equation for the line, which is here. Right? And again, these are similar things that you use for velocity. A velocity essentially is just a tangent line, or it depends. If it's average velocity, you're going to use the secant formula for it. And if it's instantaneous velocity, you're going to use the methods that you would use to approximate tangent lines with the secant formula. Okay, and I'm going to skip over this problem just for ease of time, but essentially you'll have a similar problem on the practice, and that's solved, and you can also work on it during the breakout sessions. Okay, and for the limit function, essentially what we just said is that a limit is basically, you can write the definition here, but a limit is just you take a function and you're seeing what number it approaches as you approach a certain x value, right? And it has to come from both sides. And if not, you would use a one-sided limit to see what number approaches from the left side or right side respectively. In order for a full limit, which looks like this, to exist, you need to have both of them equal. And we solve the graphical limits, which is just looking at a graph. And I'm sure you guys are kind of all right. If you don't feel comfortable, we can ask in the breakout sessions or review the recording on YouTube. And for here's where we left off. So continuing to kind of overcap of what we did so far, we're basically looking at this limit, and in order to evaluate it, generally you kind of substitute this value into the function, but because we result in something over 0, we know we can't necessarily evaluate that way. And in this case, we're kind of suspecting in a limit that results in infinity or d/e. But because it's a one-sided limit, we have to use some methods or the methods to kind of evaluate it and see. So we basically tried to plug in a number that's really close on the right side, or the positive side, of 5. And we chose something like 5.0001. And we saw when we plugged it in that the numerator didn't experience much change, but the denominator changed into a really small number. And it doesn't really matter what this number is, but we can kind of see intuitively that this will result in quite a big number, right? And that just means that it's a really big number. And so we can kind of assume the closer we get to 5, then the closer we get to a big number, and that will be infinity. So the limit for part 31, as x approaches 5 plus, from the right side for this function will be infinity. And you could do a similar thing for the left side, right? So that would be x approaches 5 minus, you would simply put, or plug in a test value that is left of the number you're trying to plug into. Okay, so I'll go ahead and clear some space and then work in 35 really quick. I should just also right there. Okay, so really quick, 35, similar thing. You see that if you plug in 3, you're going to get ln of 0. And ln of 0 is something that doesn't exist, right? Or it's d/e. So in order to kind of see where the right-hand side approaches, we're going to plug in a test value. And I would say something that's really close to 3 would be like 3.0001, right? So if you plug that in, you're going to get some 9.00 something. Again, we don't really care about the value. We just want to kind of see what happens to it. This becomes ln of some really small number. And we know that would be equal to a really negative but big number. And this would lead us to assume that as we get closer to 3, in this case, you're also going to lead closer to 0, which means that ln of 0 would be, or close to ln 0 would be negative infinity. And you can also intuitively derive this by knowing what the ln graph looks like. So that is also a method that's applicable. And for questions like this, for 12, you're finding if the limit exists at x equals 0 or pi. You're trying to make sure that these are the same, because x is less than 0, you'll have a left side limit, but for this function, you're going to have a right side limit. Same for pi. This would be a left side limit for pi for this function, and a right side limit for pi on this part. So all you have to do is plug in those endpoints, and for cosine, you would be cosine of 0, and you would test to see if they're equal. If they're not equal, that means the left side limit and the right side limit are not equal, and so the limit does not exist. So let's see. 1 plus sine of 0 is 0, and cosine of 0 is 1. So therefore 1 equals to 1. That means the limit for this function as it approaches 0 exists. And in fact, it's 1. So for pi, if we test that, we test for cosine of pi, and we test for sine of pi. And we know that cosine of pi, well, let me just bring it here. Cosine of pi is equal to -1, and sine of pi is equal to 0. So they're not equal to each other. So therefore, the limit of f of x as x approaches pi is d/n(a). Okay. And so for the limit of function, again, we have limits that go to infinity. We kind of actually done a couple problems that kind of list these, but essentially what this definitions are saying is that if we have some number, let's say a, and almost always as a vertical asymptote, if that number goes to infinity, or as large as we get close to a, and if they both go to infinity from either side, then we can say that the limit as x approaches a is infinity. And same for one-sided, but note that if they go to different values, or if they go to arbitrarily large and arbitrarily low or negative, right? They're not going to technically the same direction. That means they're not equal to the same infinity. That means that the function or the limit as x approaches a for that doesn't exist. Let me see on time. Okay, so for limits that go to infinity, again, this is an example. This one from the left side goes to negative infinity, and from the right side, as it approaches this number, is infinity. Because they are not equal, then the limit does not exist. So limit as x approaches 3, in this case, does not exist. And in some questions in the exam, you'll be asked to prove a vertical asymptote exists. And in order to do that, one of the definitions is that you must have any one of these statements, which is basically infinite limits as you approach a, and it also includes the one-sided limits. So if you want to prove this one, right, or that there was a vertical asymptote at 3, you would just have to use one of these, sort of positive, and then from the left side, you prove that one of these is infinity or negative infinity in order to prove that there's a vertical asymptote at this equation. So an example, you're going to see which numbers or which x values on this graph is a vertical asymptote, and these ones just kind of guide you through, but we can kind of just skip to the equations. We know that both at a -3, they both go to infinity, so we know that's a vertical asymptote. We know both of these go to negative infinity at -1. So that's also an equation of a vertical asymptote. Same with this one, x equals 2. And we can't tell at these endpoints. So those are all the available vertical asymptotes. And you would prove each one of these by saying, oh, okay, for this one, for -3, I could say that the limit as x approaches -3 for this function is equal to infinity. And that would prove this vertical asymptote. For this one, you could use either left-hand side or right-hand side. So next section is 2.3. Now you're going to calculate limits using these properties. And to briefly go over these properties, they should be, you should kind of learn them. So I won't go too much detail, but essentially it's saying that there's a bunch of properties you can use with limits. You can split them. So if you have the limit of two kind of expressions, if you take the limit of each individual one, then the limit is the same. Same with subtraction. And for constant as well, you can pull the constant out and you will have the same limit. The product rule also is true. This means that if you have something like x times sine of x, right? And if you have a limit to some value, if the limit of x and the limit as for sine as it approaches a, if these two exist, then it's going to be the same as this limit. So you can evaluate this way by splitting up the limits in your product rule. And then same thing for division as long as this limit does not equal to 0. Otherwise, you can't necessarily do this. And there are a bunch of extraneous limit laws that you can review on the PowerPoint if you wish, but essentially they're derived from the previous 5. So it will kind of be easy to see these intuitively, but if you need a refresher, you can always go in the PowerPoint. And then one of the main ones called substitution limit law, and it's basically what we've been doing so far. We've been saying that if it's a polynomial or rational function, that essentially means that a polynomial is just some value with a bunch of x's, some expression with has x to the power of n. A rational function is those polynomials divided by a polynomial. Then you can try to plug in a and evaluate the limit that way. And that's essentially what we've been doing so far. This property basically states that you don't have to have the point defined to have a limit. And that's kind of what we covered before, just in more specialized rules, right? So we can do a limit law example. And this is one you've probably seen on your homework as well. They're giving us limits defined, and we're to use the limit laws to evaluate these ones. So I'll skip over this one or some of these just because I think they're pretty easy. But for something like C, that's kind of derived from one of the limit laws that you saw before. But essentially, it just means that in order to solve this one, you can take the square root out and put it inside instead, and it would be the same thing. Right, and you just plug in 4 for the limit for that one, and you would get this one, and it would be the limit. Similar for this one, you can try it out, where you can split the limits using product and the division rule into multiple limits. And as long as f of x, the limit f of x is not equal to 0, and these two exist, it should be valid. So in this case, it would be g of x would be -2 times 0 times 4. And because this 4, or the bottom is not 0, it's fine even if the 0 is over here. So it would just be 0. And there should be, all these example problems should be on the review packet, which also has an answer key provided. One of the other ways to solve limit is called the squeeze theorem. And it essentially states that if you have 3 functions and you're trying to find a limit of the middle one, g, if all these 3 functions equal the same thing, at a certain value, a, then even if g is not evaluatable doing like normal methods, we can basically prove that our middle function is equal to the same value. So you're basically squeezing a function between two, and if the two functions that squeeze it are the same, then we can conclude that the function is the same. And generally, it's used to prove limits that are not evaluatable using normal methods, and it's often used during sinusoids because we know that a sinusoid always stays between -1 and 1. And that's the same for cosine x and some other trig functions, right? Because we know that it always stays between these values. It just repeats. And you'll see that in a future problem. So let's try one of these. So we have a function, another function, and a third function, and we want to find this limit. So the process of kind of doing this is that we take our existing inequality and we're going to apply the limit to all three sides. So if we apply the limit as x approaches 4 for all of these expressions, you'll see that the middle function now looks like what we're trying to find, even if we don't have a function necessarily for it. Oops, I should have put out the limit, which is 4 plus 7. And if we evaluate, we see that these are polynomials. So that means we can just plug in and use direct substitution to evaluate these. We know that this one is equal to 16 minus 9. Inside is the limit. And we know the limit for this one, if we plug in 4, is 16 minus 16 plus 7. So these cancel out. This one equals 7. We see that the limit inside is squeezed between these two values, and therefore we know that by the squeeze theorem, the limit is then equal to 4, or 7, sorry. Okay, so there are a bunch of other kind of methods that are used to try to evaluate a limit when direct substitution does not work. And the reason why it doesn't work is usually because the denominator is equal to 0. Or somehow it's equal to infinity when we encounter the x approaches infinity, right? Which is not evaluatable. So in this case, when you see things like this, one of the first things to do for rational functions is to try to factor. And we see that this is a little bit more complicated one. But we're able to factor the bottom one into x plus 2 times x squared minus 2x plus 4. But more than likely, you're probably going to factor a quadratic, so I wouldn't worry too much. But in this case, we can see that we can cancel out this x plus 2, and it just so happens that now our bottom function will no longer equal to 0, and so we're free to plug in our -2, and that's equal to x squared minus 2x plus 4. We plug it in, and we get 1 over 4 minus 2 times -2 plus 4, which is equal to 8 plus 4, which is equal to 1/12. And that's how you solve these kind of limits. So you should look out for things to factor, and especially for rational functions, because that's one of the key things you can do for these. Now, sometimes you encounter square roots, and you can't really factor these, so you'll have to use something called a conjugation. And conjugation just kind of means that if I have some square root, or the conjugate, let me explain what a conjugate is. A conjugate is essentially changing the sign for something like, so a plus b, you might have seen that the conjugate would be just changing the sign in between. And the conjugate of a minus b is the same thing as a plus b. So for this one, the conjugate for the top, for the square root, would be, I'll show it up there, would be the square root of 4u plus 1. That term doesn't change. And you would change this minus sign into a plus 3. And the conjugate kind of square root method basically helps you get rid of one of the polynomials as well. So you'll see that you have to divide both sides of the conjugate, and we know due to, if you multiply conjugate by its conjugate, you'll get a squared minus b squared. I think it's called difference of squares. We can just use that on the top one to find that the square root goes away because this a squared makes the square root disappear. And then you have minus the square of 3, which is 9. And the bottom also gets multiplied by that conjugate. But it can't really cancel out. It's not really easy to factor either, so we're just going to leave it as is. We're going to simplify the top. The top becomes 4u minus 8. We factor out the 4, which becomes u minus 2. And once we have this one, we're going to find that we have a polynomial that we can cancel. 4u plus 1 plus 3. Cancel this out. We're going to end up with the limit as u approaches 2 for over the square root of 4u plus 1 plus 3. And we see if we plug in 2, there's not going to be any problems with the denominator. So in this case, a rational function allows us to just plug in 2. You get 4 over 9 plus 3, which equals to 3 plus 3, which is just 4 over 9. Or 4 over 6, sorry. Which you can also simplify to 2 over 3. Alright. So another one that you'll commonly see is where you have a fraction as the top numerator divided by some polynomial. So in this case, you don't have to, or you shouldn't have to try to factor anything. You want to try making this numerator into a singular, or combine them together so they have a common denominator. So in this case, you have 1 over x minus 1 over 3. In order to get a common denominator, you cross multiply, which means that you cross multiply 1 and 3, 1 and x, and the denominator should be combined, which means that you have 3 minus x over 3x. Right, and then that's still over x minus 3. So in order to divide a fraction by a fraction, you might remember that there's that kind of acronym called keep, change, flip. In this case, it's the numerator you keep, you change the sign from divide to multiply, and then you flip the bottom. So in this case, we can kind of structure it like this. Divided by x minus 3. This becomes keep, change, and then flip. And you'll actually see that this cancels out because this one's actually equal to minus x minus 3. So we'll just, for sake of clarity, we'll just multiply it out and then do it. This becomes minus x minus 3 divided by 3x, x minus 3. These cancel. You get negative 1 over 3x, and you have to find the limit as x approaches 3. And because we got rid of that term that makes our whole function go to 0 on the bottom, we can just plug it in. We get negative 1 over 9. So this is one of the more conceptual but also kind of hard to grasp sections. It's the precise definition of a limit. Essentially, it's just a fancy way to prove that a limit exists by saying that if I have a function and I want to prove that the limit, let's say, I think this one is limit as x approaches 3 for f of x. We're basically going to say that, okay, if I have some distance that's defined as delta, you can see here that this distance, the small distance between 3 is delta, and so is this one. If I change, or if I'm within any range of this delta between 3, then I have an equivalent range that I can only move to from this number L, right? And this would be equal to 5. So that distance epsilon is what's given, right? So if I have a certain delta, I should have a relationship with epsilon so that if I plug in any epsilon or delta, I find an equivalent number that's within a certain range of my two values. And that's kind of defined as these two. So x minus a kind of assumes that, okay, if a is 3, that's essentially the distance here, which is epsilon, or sorry, delta. And same with this, if I have a function here, that's just the distance between my limit number, which is epsilon. So if there's some value close to our a, then there's a corresponding value to our L. And you have to prove a relationship in order to prove the limit. And these, there are similar things that you can use, or it's basically the same process to prove one-sided limits using these ones. But essentially it's the same thing conceptually. And if you want to go to an epsilon delta problem, it might make a little bit more sense. So if we find a number delta, we need to find a number delta such that this delta and this epsilon or a relationship, and we can find epsilon, or if we plug in epsilon number, we can find a number delta. So in this case, what you need to do is to turn our epsilon, or generally, in most cases, you need to turn your epsilon function or inequality to look like your x minus 2, or your delta inequality. And then you can substitute and form a relationship. So in this case, you have this one. We see that we can factor out 4 from this, and we can bring it out from the absolute value. So we get absolute value of x minus 2 as less than epsilon. We want to isolate this x minus 2, or absolute value, because that's defined as delta. We just divide 4 by both sides. We get epsilon divided by 4. So we see that we can, or this epsilon essentially corresponds to this absolute value x minus 2. And so we can say if we want to choose a delta that's equal to, would be equal to epsilon over 4. Right? So now we have a relationship. We can just plug in our epsilon values. So epsilon equals to 0.1. Then our delta is equal to 0.1 divided by 4, which is equal to 0.025. Same thing with epsilon equals to 0.01. Our delta, due to this relationship, would be equal to 0.01 divided by 4, which is 0.0025, I believe. There's a similar thing with infinite limits, right? So epsilon delta is used to prove normal limits when you have a range of numbers. But in this case, epsilon and big M is used to prove infinite limits. So it's kind of something similar. We still have a delta that is between, or is a distance between some value a. And basically what this definition says that if we have, or if we're in between that range, we should have, our function should be above some value m, no matter what m is. And it's used to prove infinite limits, and it's kind of similar. In this case, we can also use it to prove something like this. So how close to -3, or essentially what distance delta between -3 do I have to take it so that our m is equal to 10,000? And we can see it because if we see here, f of x is greater than m, kind of corresponds to this. So this is our function f of x. So if we know that this is true, we're trying to find a number delta that corresponds to our m equals 10,000. So let's write the definition of delta. It's x minus a. And we know in this case a should be -3. That's less than delta. And this is essentially our f of x is greater than m definition already. So what we have to do is we have to basically make this function kind of look like our allegorical function. So this would be x plus 3 is less than delta. And we see that if we want to isolate this x plus 3, we're going to have to play around with the inequality. Right? So in this case, we can multiply this whole thing to the other side to get it out of the denominator, and also divide this by 10,000. So that would be 10,000, or sorry, 1 divided by 10,000 is greater than, and since there's no negatives, we don't have to change the sign. It's by x plus 3 to the power of 4. And in order to get this x plus 3 by itself, we're going to take the root, the fourth root, on both sides. And as you remember, if we take any square root or any even root, we have to do a plus minus. But we know that in this case, we can place an absolute value to mimic the plus and minus, because we know that it's pretty similar in the definition. So this would be 10 is greater than absolute value of x plus 3. And so therefore, we know our delta is defined as the absolute value of x plus 3. And that should be, that means we can correspond the relationship to be delta is equal to 1 over 10. And so this is the number, so this is the range between -3 that we can take in order to be above 10,000. So if we're here at -3, and where our delta is 1 over 10, that means 0.1. So this would be actually -2, or -3.1. Let's see, -2.9. We're always going to be above 10,000. This function. So that's essentially what this question means. And if you're asked to prove a limit of affinity, that's also a similar thing that you would do. Essentially, you would use these two relationships and find a delta and big M relationship. So continuity, the definition is a function m or f is continuous if the limit and the defined point are equal. So that's essentially using limits to kind of prove continuity. And continuous can be one-sided as well. If the left side limit is equal to the defined point, then it's continuous from the left or right in this case. And it'd be continuous from the left if the left side limit is equal to the defined point. And there's 3 criteria you need to check. F of a must be defined in the domain of the function. The limit as x approaches that a must also exist. And the final one, which basically mimics this one, means that they must both be equal. These 2 criteria must be equal to each other. And that will make it continuous. Yep, and these are all a bunch of definitions that might be nice to know, but they're not required. It's essentially saying that a function can be continuous on an interval if it's continuous in every number on the interval. So that may look something like this. Function. So if this is a and b, then we can say that a, b is continuous because there's no point that is not defined on this interval. And these are just some theorems stating what you can look for or what kind of functions are continuous. And they're nice to know, but you can kind of look, or it's a little bit more intuitive. So you can look these on the PowerPoint if you need it. So a better thing to kind of look for is discontinuity. So on a graph-wise, there's kind of three types of discontinuities. If there is a hole, which is usually found in a rational function where you can cancel something out. So let's say like x plus 2 times x plus 3, and you cancel out the x plus 2. Essentially, your x cannot be equal to -2, which will make this 0. But the function still exists, and that will be a hole. Infinity is when you have some vertical asymptote. So let's say you have this one. It means that basically at this value for a rational function, your function will go to infinity from either side, or if it stops. The jumps are basically when you have piecewise function that don't connect. So this could be a different function, and this could be a different function on the same kind of f of x function, but they don't connect at the certain endpoints. So some problems, you might see a graph and be asked to state when it's continuous. And since we identified all these discontinuities, we essentially list the intervals where we don't see it. So from the graph G, state the intervals in which G is continuous. You'll have -3, and we have closed bracket because it's defined, and where we see it's continuous until we hit -2. And it's open because it's a hole. And we're going to put the union sign, which just means that all these intervals are for the function. And we see that from -2, it's continuous all until -1, but it never really stops. So we can say that it heads towards, well, actually, hold on. No, sorry, that's for a range. This would be continuous until -3. And this would be open as well, because infinity never reaches a certain point. And then union, and we have -3. And it stops at 0 because there's a jump. And that 0 is defined, so we have close bracket. And then it's unioned with open 0 to 1. Even if 1 is defined, it's not at any of our limits, so it doesn't count as continuity.
Excuse me?
Yeah. I think some of the tutors said I meant -1, not 3.
Yeah, I was gonna say that it's you.
Yeah, sorry, you're right. It's -1.
I think you.
Yeah, thank you for that. Yeah, good point. Thank you. Okay, and then so we have 0 to 1, and then it's union with the last continuous interval, which is from 1 to 3. Oh, I think someone else pointed a typo. -1 to 0. Oh yeah, my bad. Definitely right. This is -1 to 0. Sorry about that. But you should have practice problems, so sorry about that. Okay. And then one of the questions you might be asked to find is that you want to find some value for a piecewise function that makes everything continuous. So that means we have to focus on these endpoints to make sure that these are continuous, and we can use, or essentially want the limits and the defined points to be equal to the same thing. And this is basically, you're going to use system equations, but that happens after we kind of find these endpoints. So if we want these endpoints to be the same, then if we plug them in, we get c times x squared, right? Because this endpoint 2 is 4 plus 2 times 2 is 4. And then this should be equal to this endpoint when we plug in 2, which is equal to 8 minus 2c. So if we simplify it, we get 4c plus 4 is equal to 8 minus 2c. And we move these variables around. We want c on one side and all the other numbers on the other. We get 6c, and we're going to move this forward to the other side as well. We get 4. And to find c, we just divide by 6. And we get 4 over 6 is equal to 2 over 3 after we simplify. And if we plug in this constant, we'll find that if we evaluate 2 for both functions, we'll get the same defined point at 2, and also the limit at x approaches 2 will also be equal. So intermediate value theorem is essentially a theorem that kind of uses continuity, that says if a function is fully continuous, then if we have a range of values, such like a, b, and they don't necessarily have to be in closed brackets, and we have corresponding function values, that if we have some number between f of a and f of b, that there should be a corresponding x value between a and b. So you can find at least one value. If we want to find n, there's at least one value c that's also in the function. And there can be multiple. And most commonly, this is used to find roots within an interval. So if you want to prove that there are 2 roots in the interval -1 and 1, and you don't want to actually solve for roots, then essentially you would plug in all these values in these intervals, like f of -1 would be equal to 9 over 8. If you plug that in, f of 0 would be equal to -1 over 8. And f of 1 would be equal to 5 over 8. We can kind of use these to say that, okay, so we know we're trying to find f of some value x is equal to 0. So therefore, if we have some value c, f of c, between 2 points, by intermediate value theorem, we can prove it. So in this case, we know that if we want to prove that there's a root between -1 and 0, there's 9 over 8, 0, -1 over 8, and this, by IVT, it proves that there should be some point c in between. Okay, you can see I'm kind of going long on time, so I'll try to hurry. We're almost done. We have just a couple more slides. For limits at infinity, sometimes, by nature of our expression, the function, as it heads towards some really big number, which is basically infinity, you'll always approach some number L. And sometimes you won't. Sometimes you always go up to infinity, but sometimes you'll hit a horizontal asymptote, which is what's defined. And similar to your vertical asymptote, in order to prove that there's a horizontal asymptote, you need to prove that these exist. And some special infinite or horizontal asymptotes you may be expected to know are these ones. So you can use them if you forget them, but essentially it's what the arctangent goes to as you hit both sides. And similar to limits at infinity, if you have some limit that approaches infinity, generally anything that's under a polynomial whose power is bigger than the numerator will be equal to 0. And that's because as you head to infinity, you know that polynomial will also be infinity, and this 1 over some really big number will eventually approach 0. So one of the methods you'll use to solve limits that go to infinity is also called reciprocal method, and we'll go over that in the next example. So for this one, we know that we want to find the power of, or the largest power in the denominator and divide, or use the reciprocal to multiply both sides. That's 1 over x cubed divided by 1 over x cubed, as you see here. And in this case, we're going to get 4 plus 6 over x minus 2 over x cubed, all divided by 2, minus 4 over x squared, plus 5 over x cubed. And if we take the limit as x approaches negative infinity, we'll see that that theorem that we used before, anything that's divided by infinity will be equal to 0. We can cancel all these out, and we're left with 4 divided by 2, which is equal to 2. And that's how you solve these kind of limits. And if you remember, sometimes we can't exactly do it numerically like this. We kind of have to use intuition. If we plug in infinity here, we know that e to the power infinity will essentially be infinity, because it's just the big number, which is like 2.71 approximately, that's raised to a really big number, will just approach infinity as well, right? So arctangent, or tangent inverse, however you prefer, we saw that before, that if it approaches infinity as well, then it will reach a certain value. And if we go back, we know it's pi over 2. And so that's why we kind of use those, or we memorize those values, because this function, as it heads towards infinity, will be pi over 2. And that's just one of the special kind of trig functions that has that horizontal asymptote. And then here's another application of squeeze theorem in this case. So as we stated before, squeeze theorem just means that we're squeezing, or we're using this kind of set of inequalities, and we're trying to put the limit inside the middle. Okay, so in this case, we know that, oops, so we know in this case that sine of x is always between these two values. And that's kind of just a given proven identity. We're going to use this equality to make the middle look like this. And we're going to evaluate the left and right side. And if they are the same, then we can prove that this limit exists to be equal to that value by the squeeze theorem. So I'm just going to apply the squared. And we actually know that we should probably actually use a different equality, because we know that sine squared of x also has its own equality, which is it's between 0 and 1, I believe. And if we use that one, we're going to apply, or we're going to divide all sides by x squared plus 1. And then, because this function looks like this one, we're going to now apply the limit as x approaches infinity to all three. And we know that this one goes to 0. Sine squared x. And that's x squared plus 1. And the limits of 1 over x squared plus 1 as x approaches infinity as well. We'll see that this one goes to 0 by nature of a constant. The middle stays the same. And this one, because you have 1 over infinity plus 1, is basically also 0. So by squeeze theorem, because they're squeezed between these two values, it's equal to 0. This one's equal to 0. And that's kind of how you solve limits that go to infinity with any trig function that kind of looks like sine or cosine. And essentially this is...
Oh, I had a question.
Yeah, the question?
Yeah, so would that be the same for like if it was a problem with cosine, we do just put it in
Oh
between
yeah.
0 and 1?
So cosine also stays between 0 and 1, right? So
Okay.
that's also something you can do. Yeah.
All right.
It's -1 and 1. And if you have cosine squared, I believe it's the same thing as sine squared, which would be
Okay.
0 and 1. And most likely you're going to use sine or cosine, I think. And one of the twos also says that cosine or tangent is also pretty popular. Or arctan, okay. Arctan is between, I believe. Oh, hold on, that's not quite right. I think there should be one for arctangent, but I'm not too sure. Okay, one of the tutors says that it's between. Oh yeah, that makes sense. It's between -pi/2, pi/2. But most likely you're probably going to see cosine or sine in this case. So these are basically if you see one of these cosine, sine, or arctan, essentially you can use the squeeze theorem if it goes to infinity. So last kind of practice question is essentially proving horizontal and vertical asymptotes. I'm probably going to cut it pretty short because I want to give you guys more time for practice questions. But without, or essentially you find the horizontal and vertical limits. The vertical one is essentially you want to make the denominator equal to 0 and find what x values that equals to. For the horizontal ones, I believe you just take the limit as the function goes to infinity and negative infinity. And you usually have one or two of these. They're most likely the same, but that's not always the case. For example, if you had the limit of ln x, you would know that if it goes to negative infinity, it goes to negative infinity and it changes for infinity, like that graph. Okay, so for this one, if we solve for the bottom for 0, we factor it out. We get x through x plus 5. In order to be 0, our x is equal to 0, or I think that's -5/3, right? And if we found these vertical asymptotes, but in order to prove that they are in fact vertical, we must use that property or that theorem, which says that we must find that the limits approaches to infinity, whether it's left-hand or one-sided, or the real limit. So I'll solve one of these because I think the other ones are not too different. But if we find a limit as x approaches, let's say 0 from the left side, we put the whole function in there. I'm going to leave the bottom factored. So that's x times 3x plus 5. We'll see that again if we want to plug in a test point that's less than 0. We could do something like -0.001. And we see that the top is quite small. 1 squared plus 5. But that constant is still quite large here. So it doesn't really matter what the numbers are. We just want to see what happens to it. And we know that we have 0, 0, 1. And this is essentially 2. We know that as this one goes closer to 0, which means that it gets smaller, we're going to approach infinity. So because this limit approaches infinity, we can prove that there's a vertical asymptote at x equals 0. And in order to solve the horizontal asymptote, or prove that it exists, we use the limit as x approaches infinity for the whole function. Oh yeah, another question? Okay. You're going to use the reciprocal method, and that will get you what you need. So the highest power in denominator is 1 over x. And we can kind of see, once you do all the math, it's 1, 0, 0, because those go to 0, over 3. And so you get 1 over 3. This is your horizontal asymptote at y equals to 1/3. Okay. And that should be all the slide material. If you have supplemental resources, you can look through 2.1 to 2.6, or you can also go to this website, which is also really helpful. Okay, I think we should, I don't know if we have time for a break or if you guys just want to go straight to the breakout sessions. Slide 41? Yeah. And if you need to kind of review, there should be recording, but there's also slides in the shared content. If you go to shared content and share files, you should be able to download the PowerPoint and the practice problems and all the answer key. Okay. Is there any questions? I wasn't looking at chat, but I think the supporting tutors should help. Okay, I think we should start breakout sessions. Okay. So we're going to go, or I'm just going to show these practice problems. You should have access to in share files if you want to look through these and see what kind of practice problems you want to, or you would want me to demonstrate. So go ahead and type in chat if for any like certain topics, I can go to the questions. There should be a question for each example problem we did on the slides. So if there's any questions on the slides that you were confused in, or any topics, we can go over it, or more practice problems. Yeah, horizontal asymptote. Okay, gotcha. So for horizontal asymptotes, the main method you're going to use to evaluate them is called the reciprocal method. So essentially, a horizontal asymptote, you need to prove that the limit as x approaches infinity for f of x, some function, equals to some number, and that number is just infinity or negative infinity, then that horizontal asymptote does not exist. Or there is no horizontal asymptote for that in that case. Right? So when you try to evaluate that, most commonly you're going to see something like, something like this, right? It's a polynomial over polynomial. You're going to look for the highest power or of the denominator, and you're going to use the reciprocal and multiply both sides by it. Yep, what we just said. So L for as x approaches infinity or negative infinity, and oh yeah, it has to be negative infinity as well in order to be a horizontal asymptote. And which one of these do you want to try, or do you want me to demonstrate? Because there's quite a few, and not all of them use the reciprocal method as well. Did that answer your question, by the way? I can explain more if you still need it. Okay. So essentially, in order to find a horizontal asymptote, generally a function kind of, as it approaches a really big number on either side, sometimes it can stop at a certain value, and that will be something like L. And so in order to find it, you need to evaluate a limit of that function. So let's say this f of x, right? Something like that. You have to evaluate the limit as x approaches infinity for that function. And let's test it with 25. So if we want to evaluate this one, we know that the biggest power on the bottom numerator is x, right? And so we're going to multiply the top and bottom by 1 over x, which is the reciprocal. That's why it's called the reciprocal method. So in this case, oh, sound isn't working. Can everyone hear me? All right. Okay. You might have to restart your system or change the settings a bit, but I'll have to continue on. And you can also review the YouTube if you want to watch the section over. But essentially, if you're going to do this, this problem's a little bit tricky because you have a square root, right? But we know, and as a hint here, that 1 over x is equal to the square root of 1 over x squared for all positive x values, right? And so we can transform this one or use this equality to put this reciprocal into the square root. So that will look something like x divided by x squared plus 3x squared divided by x squared. And the bottom will be 4 over, or 4x over x minus 1 over x. I'll just use this space here. And so these basically kind of cancel out into being 1 over x plus 3. And this is 4 minus 1 over x. If you take the limit as x approaches infinity, so we're kind of assuming that's 1 over infinity approaches 0. And it's not equal to 0, it just approaches it, right? Because there still is a limit. We just substitute the limit in. So anything below x, or is divided by x to some polynomial, right? It could be squared if you want to, would be equal to 0. So these can basically cancel out when we substitute or evaluate the limit. And so this is equal to square root of 3 divided by 4. And so this is the horizontal asymptote. And if you look at the graph of this, as you approach infinity, it's going to approach square root of 3 or 4 indefinitely, right? So that's why commonly used when you list the horizontal asymptote, you're going to use y is equal to root 3 or 4 or whatever horizontal asymptote you find, right? Yeah, and you can do it to negative infinity as well. You don't really need to do this above process because we already have the same thing. You use the same process, reciprocal. And if you plug in, let's say, negative infinity to here, right? This would be, or 1 over negative infinity still approaches 0, right? So that wouldn't change anything. And same for this one. You would just get same square root of 3 over 4. And this is also, or the same horizontal asymptote. Right? And then when they said they want you to prove that the horizontal asymptote exists, we pretty much already did that by using the limit of this one, right? Because one of the definitions was that if this limit exists and it is equal to a certain number, then the horizontal asymptote is defined as that line, L. Does that make sense? So if we try it with the other problems, we'll see that we can't really use the reciprocal method, I don't think. Oop, didn't catch them all. So for number 30, right? Why wouldn't the asymptote approaching negative infinity be negative? Okay, so I'll write that again. So we found that transform expression, right? Which was, I believe it was 1 over x plus 3 over 4 minus 1 over x. So if we plug in, or see, not really plug in, but we try to see where it approaches as we plug in negative infinity, this one would approach 0. It wouldn't leave any negative value, even if we're approaching negative infinity, because what this negative infinity does when it's plugged in actually just makes it approach 0. So there's no like change to the whole entire thing. This negative infinity still just turns it into 0, and it doesn't actually change the values that we have right now. Does that kind of make sense? Oh wait, would it be negative infinity? Let me see. Oh, okay. Is that what you mean? Okay. TA is saying to add a negative sign before the square root. Oh, okay. Yeah, sorry. That's why the hint was there. Yeah, my bad. Okay, you're exactly right. So that has to do with if we want to put inside the square root, in order to make this not an imaginary number, your x value, this is equal to, for all x's less than 0. That's because you plug in something like -1, be -1, and this would be also -1. Yep, sorry about that. That's my mistake. Yeah, that was why the hint was there. Forgot about it. Yeah, but if you had negative infinity, then you're exactly right. You would use, this would only apply to things with square roots or even square roots, because you have to make sure that you have that negative there. Because for all negative x's, this equality is the one that's true. Yeah, thanks for catching that. So in that case, it would be, you'd have a negative out here. And that would make it negative square root of 3 over 4. Okay. So that would be the other horizontal asymptote. Okay. Do you guys want to try any other of these questions? We can do more of these horizontal asymptotes if you want, or we can do any of the previous questions. Number 40? Okay. So for 40, you're taking it to a one-side limit for 0 to the right. So in this case, one of the property limits is that you can kind of put them inside functions. So tangent of arctan as x approaches 0 positive for ln x would also be equivalent, right? So in this case, if we did this, if we put in a test value, right, 0.001 for ln of x, as we recall, the graph of ln x does this as it approaches 0, right? So it goes to negative infinity as you go really close to 0 from the right side. So essentially, you have tangent arctan of negative infinity, right? And we recall that this is a certain type of limit or horizontal asymptote. We know that this is equal to negative pi over 2. Does that make sense? And it has to be, and the reason why they put that 0 plus there is because ln does not have any other, it doesn't have a left side limit at all. It doesn't exist. So that's why they have that plus there. But it doesn't really change. Anything else you guys would like to try? And note that the answer keys should also all be here. What graph should we memorize for the test, like sine, cosine? I think it would be good to memorize or kind of know what all those graphs look like, particularly at least this inequality is pretty important. I'm not too sure about inverse of sine and cosine. I don't think you need to use those necessarily. It might be helpful if you want to feel assured. Arctan, you do have to know that the limits or the horizontal asymptotes of those, right, is between negative pi over 2 and pi over 2. Because if you take the limit, it would be one of these, right, just as we did before. ln x is good to know that as you approach 0, it's going to go to negative infinity, and if you take the limit as you go into infinity, it just kind of goes to infinity. So those are all good ones to know. For example, like for cosine x in this one, you need to use the inequality that we had before with squeeze term. And if you want to go over this problem, we can. But is there any other questions? Just let y'all browse. But these are essentially questions from the textbook, and I tried to match them with the home questions on your homework. So if you want extra study material as well, aside from this practice packet, you can look for similar questions that, yeah, sure. But you can look for similar questions to your homework and kind of this practice problem in the textbook, or any questions online. Okay, so we can do number 39 again. Just erase this. So for this one, the hint is to use squeeze term, and that's basically because we need to use this property or this inequality to solve it. And note that if we tried to plug in infinity normally, that we know that this one would go to 0, but the limit of cosine x as x approaches infinity actually does not exist because it just keeps fluctuating over and over, right? So that's why we had to use squeeze theorem in this case, and not any of the other limit laws. Okay, so let's use it. So we're going to start off from this inequality, and our goal is to make this middle part look like our current limit here. And as long as these two values that are on the sides of it are equal, we can prove that the limit exists using the squeeze theorem. So in order to transform this function, first we start with the inside. Okay, in order to make this cosine look a little bit more like this expression, we're going to multiply all the sides by e to the negative 2x. So this becomes negative e to the negative 2x is less than e to the negative x times cosine x. And this 1 becomes e to the negative 2x. So we have this inside. Now if we apply the limit as x approaches infinity to all three, we're going to get something like this. And that needs a limit there. Right? And in order to evaluate the left one, we know that from our exponent rules that a negative exponent means that it's actually, or it basically is flipped, right? So negative e to 2x is equivalent, or sorry, negative e to negative 2x is equivalent to 1 over negative e to the 2x, where we change the sign, right? So if we plug in infinity here, we know that e is really just a number, right? It's like 2.71 something. And if we have that raised to infinity, we're basically going to get 0, right? 1 over some really big number, even if it's negative, is equal to 0. So that's on that side. Let me just make some space here. We're going to get 0. That limit stays the same inside. And this limit also evaluates similarly, where it's basically the equivalent of 1 over e to the power 2x. We plug in infinity, and that's e to the power infinity, which is essentially 1 over infinity, which is 0. And so we know that it's sandwiched between these two values, right? That means by squeeze theorem, right? This limit is equal to 0. Does that make sense? And graphically, we know that the cosine multiplied by this one goes to 0, so it's kind of like, essentially, it keeps oscillating until it hits 0. Any other questions? Okay, so ln of 0 goes to negative infinity. Yep. Ln of what goes to positive infinity? So if we look at the graph again for ln, we actually see that there's nothing stopping it, and it actually just goes to infinity. So limit as x approaches infinity for ln of x is equal to infinity. Does that make sense? So it just keeps rising and rising. Any other questions? Do you guys want to go over anything specific? Any concepts? What is the limit of sine of x approaching positive and negative 50? Okay, so kind of similar to cosine. Like any sinusoid function, because it's something that repeats over, it doesn't have a limit. It will always stay within -1 and 1. So no matter how far you go, it's just going to keep oscillating. And so that's why when you take the limit of sine x or cosine x as it approaches infinity or negative infinity, it's not a limit that exists. So it's d and e. Because it never stops at a certain number, it always keeps moving. And same for the left side, right? It just keeps oscillating no matter what, and it won't stop. Does that make sense? So the reason why we have something that stops for arctangent, for tangent of our inverse tan, right, is because if you look at a unit circle, we know that arctan defines the angle, or the answer to an arctan is the angle of some slope, right? Some slope x. So if we look at kind of the unit circle, if we increase our slope, which means it's getting steeper, like so let's say we have x is a really big slope, or infinity, right? It's basically going to be a straight line because it's going to be so steep. And we want to know the angle of that infinite slope. The angle that it approaches is pi or half. And same with a negative slope, right? A really negative slope is going to be super steep on the opposite side. And that's going to approach the angle negative pi over 2. So does that make sense on why that's there's a horizontal asymptote for arctan? You can also just memorize it if for this one. Yeah, you have another question? Okay, in order to prove an asymptote. Oh, is that okay? How many limits do you need as a proof? I think by what the book says, to prove a single asymptote, you just need one of them. So for vertical asymptote, you just need one of them. Oh, do you need two? Okay. I guess you need to. Let me check the PowerPoint. I think it should. This is. Okay. And so what the tutor says there is that you need two limits. For horizontal asymptote, you need both limits as one heads to infinity and negative infinity. And I'm checking the blue one. I think for vertical asymptotes, the book definition says at least one. So I think for horizontal asymptotes, you need two. You need to check both the limit as x approaches infinity and the limit as x approaches negative infinity for horizontal asymptotes. But for vertical, I think the book says at least one. So basically, if you have at least one of these statements, and note that so it's a little bit messy. But if at least one of these is true, then you can prove a vertical asymptote. So let's say you had like a split function or one that kind of looks like this. If they're different, you can't necessarily use the limit as x approaches just a. It has to be a one-sided limit in order to prove it, right? So you can use either the left-hand side, or you can use the positive side, right? And any one of these will prove that there's asymptote. So for vertical, you only need one of them. For horizontal, there could be multiple asymptotes. Because as we saw in that previous question, I think there was two kind of asymptotes. So one for the right side, towards infinity, and one towards the left side. Right, so in this case, there's two horizontal asymptotes. One would be up here, and one would be up here. Does that make sense? Do you have another question? Oh wait, no, it's from before. Okay. Is there any other questions you want to go on these practice? I would say if you want to, there is the file and share content on the bottom third tab. You should be able to download the files, and that includes the PowerPoint, the practice problems, and the answer key. So it's basically, this is the practice questions if you want them. Yep, Kelly, what question do you have? Two point one? Okay, let's go to it. Which one? Is the tangent problem or the velocity problem? Oh, entry to limits? Okay. This one, or is it the limit laws? Okay, so you say, so in order to evaluate the limit at a given point, could we do an example in which we subtract from the x value in order to figure it out? Yeah, so kind of like a one-sided one. So I would say 36 is a kind of example of that one. Okay. So whenever you kind of have these one-sided limits, sometimes you have to plug in a test value, right? So this one says 0 plus, and this means from the right side. So it doesn't quite matter what value you pick as long as it's very close to the right side of the number that's approaching, right? So I could use something like 0.001. You could go further, you could go less, but probably stick to like maybe 2 or 3 decimal places there. And you're going to try to plug it into the function. So in this case, if I have limit as x approaches 0 plus, I'm going to kind of plug in this value. So test value, right? 0.001. We know that this sign, if it's very close to 0, right? Something like here, and we're approaching 0, we're going this way, right? So we're approaching, and our sign is a y value, so we're approaching 0 for this sign of x. So that means this essentially evaluates to 0, positive again, and we have ln 0 plus, and our test value, we know that if you need it, we're essentially thinking of, okay, if this heads towards 0, this is really big negative number, and if you put it into your calculator, right? Really big negative number. If you get closer to 0, you're going to get bigger and bigger negative numbers, and so you know that the direction is essentially towards negative infinity. And you don't need to essentially necessarily do that if you know that already that as you approach 0 for ln, if you know what the graph looks like, you can kind of assume that it heads towards negative infinity anyway. So this, because we're approaching 0, in this limit, we're approaching negative infinity. Does that kind of make sense? I think for these type of questions, you have to kind of use your intuition, kind of think about it. If you know what these graphs kind of look like, it's a little bit easier to do. But the test function or the test point works just as well. So if you plug in a test point, you kind of use a smaller one and then see what direction it's headed. So you keep getting closer to 0, and you know that, okay, we're seeing a pattern that it gets really infinitely negatively big, then that's kind of what we assume to be negative infinity, right? If it doesn't stop at any certain place. In the graph above, what would f of 2? This one or this one? I think you meant this one because f of 2, top one? Okay. So f of 2 would be 1. Yeah. And that's because when we say f of something, that point has to be defined. So although we know that the limits at 2 from left and right are different values, the f of 2 specifically would be 1, because that is the point that's defined there. So we can't say the limit as x approaches 2 for this function is equal to 1 either, because note that the limit doesn't matter what's defined. It just matters that the left-hand side limit is equal to the same thing as the right-hand side limit. So as long as they're equal, then that means the limit is true, or the limit exists and is the same value. Does that make sense? Yeah, and for continuity, note that both the limit and the point has to be defined. So you can find some of those questions, I think, in the continuity chapter. Kind of this one, right? Yeah, it's okay if you unmute. It's fine.
Hi, my bad. Are you open to answering, evaluating questions that practice questions that I've received from a different source?
It's definitely okay in normal hours. So this is a specific exam review. I think we stop at 9. But if you come in to peer tutoring or virtually on Saturdays, you can definitely use like other questions as long as it's not on from a quiz or test. That's from your class.
Okay,
So
thank you.
we open from, I believe, 10 a.m. to 6:30 on weekdays, and it's under the library at on campus.
Okay, thank you.
So sorry I can't answer this time, but
No, that's
you can
fine.
definitely do tomorrow. Can we do a velocity question? Yeah, we can do it real quick. Yeah, and then it should be. Okay, let me see. So velocity question. Let's do it real quick because I think we end in 4 minutes. So essentially, velocity is basically, or average velocity, right, is a secant line. So you're basically going to use the slope formula that you've kind of always known, right? Except using their functions, right? So in this case, if a ball is thrown into the air with 40 feet per second, you don't really need to know this part. You really only want to focus on the distance function, which is this. You want to find the average velocity, so that means we're using this equation for the time period beginning when t equals 2 and lasting 2.5. So in order to find these bottom x values, right, or equals to t, so this can also be t2 minus t1, you would read the question, and in this case, it begins at 2, and the other interval lasts 0.5 seconds, so it's 2.5. So these are your two t values, right? And essentially, you would plug in those values, and I'm going to do 2.5 minus y to 2 divided by 2.5 minus 2, right? Same thing with I. This one lasts 0.1 seconds, so it has to be starting from 2, lasting until 2.1. And essentially, you just plug those in to the equation here, right? And it's 2.1 minus y of 2 and 2.1 minus 2. And you're going to get so close. The 2 points are getting really close together as when you get to 4 that you could probably estimate a velocity when it is at t2 plus 2. Right, so as the closer you get, the more accurate the instantaneous velocity, or the tangent line, is essentially what it is towards t. And the answer should be in the answer key if you haven't already downloaded it. But I think it was around something like 1. I'm not too sure. It's essentially heading towards some value. Does that make sense? So you're basically kind of doing a similar thing, but it's just change like words and definitions to get you kind of understand that average velocity is basically a secant line, and instantaneous velocity is basically the tangent line for that point. Does that make sense? Yep, and I think that ends the exam review. Again, before you leave, if you want to, if you go to the third bottom tab and share files, you should be able to download all the kind of materials. There should be one practice problem packet and one answer key, and all the PowerPoint if you need it. Other than that, I wish you guys good luck on the exam. Yep. Sorry about the late start. It was kind of some technical difficulties. How do we download it? Let me see. Go to share files. There should be 3 dots, and you should be able to download it. Let me see.